first of all, thanks everyone for participating and coming, right? And yeah, as performance challenge has finished, it was our sixth challenge. We usually wrap it up with the summary session, where we'll basically explore all the optimizations that were found during this challenge. Yeah, in general, it is a good opportunity to pick up some new performance improvements, optimizations, and techniques, right? And mostly it will be a technical session, so it's good, right? It's sort of a performance deep dive analysis. So I like those sessions. By the way, if you want to chime in, and I actually basically encourage you, to participate in the conversation. So whenever you hear me, talking some nonsense, or whatever you hear I made a mistake, feel free to correct me. I don't want this to be just me talking. So please, you guys are the experts, right? You spend a lot of time working on the problem, so there is no one better than you who knows, right, all this stuff. So here we go. All right, one slides, right? So so this time actually there was I guess around 20 participants, and I received roughly 10 solutions. And the task for the challenge was word count, right? So basically the problem is you have to split a text and count each word's frequency, and then print the list in the according first the frequency, and then if there are ties, then you have to compare them lexicographically and basically output the results, right? So, and the dataset was large. It was a complete snapshot of Hungarian Wikipedia. It was 5.4 gigabytes, right? Again, all the links are here. You can take a look at the blog post with the announcement, as well as the code repository. But by the way, you can still try it on your own later if you have missed the challenge. Right. So the motivation is that so the idea for the challenge was proposed by one of the readers of my mailing list. Well, okay, so he basically said, look, we have a problem, right? Which you can fix in many languages, and for some reason, just C++, was lagging behind. But this was even not the primary reason, right? Why it caught my attention. It's just I thought that just by looking at the baseline solution, I thought that, well, we can do much better. And yeah, and as you will see actually later, like careful performance engineering and performance analysis could make a difference, right? So again, the goal for me showing you this slide is just I want to kind of break this belief, by the way, which is actually quite common among many engineers, is that, well, if I write like well, the most simplest code, it will be optimal by default. However, unfortunately, usually it's not true, right? So the reason for this slide and the motivation for me was that, hey, there is a plenty of room at the top, right? I mean, you can go far in terms of optimizing your code, and most of the software is not optimal by default, like no way, okay? And you will see later why. And so here's the baseline implementation for this problem, okay? And this is, I think, what you will typically see. Well, like if we would have access to the LeetCode database, I think will be like 95% of all the solutions, all the passing solutions for that problem, right? On LeetCode. Well, the code is quite simple. You see, it's like 20 lines of code, right? Maybe less. Yeah, and it can be, it can be, broken down into essentially 3 parts. First, you have to parse the file and kind of tokenize it into strings, right? So you essentially have to find all the strings, and also you have to you have to count their frequencies, right? Because that's the first factor which you will use to sort them. Then the second step, well, which I call actually aggregating, right? So you essentially dump all the information from your hash table into a sequential array, if you will, right? It's just a collection of pairs of word itself and its count. So you dump it into the vector, and then the third part as well is basically sorting, right? And you can see where we spend the most of the time. It's basically parsing and hashing. Okay, I think that's here. By the way, if you have any questions or comments, feel free to interrupt me, chime in, and let's have a conversation. So again, this is just a high-level view of the problem, right? So just that we are all on the same page. And for those people who will be watching it, and for those who didn't actually participate, so right. So we parse, right? So this is just an example, right? So we need to basically, to find all the white spaces, the tab and end of line characters, and those will be our separators, and that's how we separate the words from each other. Then we put them in the hash table just to count their frequencies, right? And then the third step is aggregating, where we, as I said, right, we put them together so that now we can sort them, and we sort them, right? Pretty simple. Here is again, the high level view, just a high level, right? We will dig deep into the details later and how you can optimize it, but just this slide is like answers the question: what are the high level bottlenecks in each of those steps, right? So in the parsing, well, we have what problems do we have? Well, first of all, the input file is very large. It is prone kind of to excessive memory copying, and later you will see how it can be fixed. When it comes to hashing, the hash table itself is really large, right? So it's more than 1 gigabyte, typically in most of the solutions. So again, what are the other problems, right? Well, obviously it's a hash table. You have to find a good hash function. And as you know, the baseline implementation for the standard hash map, unordered hash map, uses the how it's called, chain. So essentially every bucket has a linked list of it's a chaining, right? So if you have collisions, then you have trouble, right? You will be chasing the linked list. So it's quite likely that you want to re-implement it in open addressing style. Then let's see. Oh yeah. Then the problem is how do you store efficiently strings in the hash table? And there are many ways how you can do that actually. Like different solutions done it in different ways. So it's just in general nice to see people's approaches, right? From the CPU perspective, I think I actually ran a top-down analysis on both of the steps, and I saw that, well, in hashing, obviously, well, DTLB misses is fine. I mean, we will take a look at them later, and also DRAM latency, right? So it's because when you hashing, you essentially performing a random access memory, a random memory access, right? So that's the problem. You will constantly miss in the cache, and as well as in DTLB cache, you will be missing a lot as well. But then the third step is aggregating, right? Well, this step it doesn't take much time, but anyway, again, so you can use this step actually to prepare for and allow efficient sorting later. And then the fourth step is sorting. And here, here essentially all you have to do is find a way how you can minimize amount of work that required to sort the collection, right? And as you use something like quicksort, you will always be hit by a lot of branch mispredictions. So that's what you need to look for. So this is the overall top-down analysis. We will not spend too much time on that slide. If you know top-down analysis, that's good. If you don't know, then I think the bottom line here is just the whole application is bound by DRAM, right? So essentially, you can view it as well. A lot of CPU cycles is wasted due to the CPU not having the data, right? And it was waiting for the data a lot of time, and essentially could not make forward progress, right? So that's kind of the high level problem. Again, here is the roofline analysis. Again, if you're familiar with roofline, that's good. If not, then you can view it. You can look at it as this is basically an assessment of our application against the hardware capabilities, right? So those horizontal slopes as well as those inclined lines, those are our roof lines, right? So those are the theoretical limits of well, this was basically my machine. So those are the theoretical limits of my particular setup, right? And you can see we're doing quite poorly, right? The arithmetic intensity of the code is quite low. Well, arithmetic intensity is just how much operations you are doing for a single, let's say, byte of memory that you fetch, right? And then you can see that for example, for the most important bottleneck in our program, right, which is parsing and hashing, well, the dot, the red dot is quite low, right? So it basically it gives you a feeling of how much headroom do you have, right? And there is a lot of room for optimizations in this case, right? Sorting is somewhat better, but I mean, still, as you will see, we can do much better. By the way, any questions so far, guys? And I see 2 comments in the chat. Would the recording be shared for everyone's reference? Yes, of course. It will be uploading to YouTube. What tool is used to do roofline analysis? Yes. So I've done that using VTune, I'm sorry, Intel Advisor. Well, there are open source tools which you can use. So far, my experience was really bad with the open source tools. Advisor seems like a good option, and it is a part of the One API package. So you can I think use it for free, or maybe there is some limited licensing, but yeah, I mean, so you can use it. So again, the tool is Intel Advisor. Any other questions before we move on? And then that's nice. But by the way, so you will see later, the same roofline analysis for the optimized version, and you will see how those dots are were moved up. So essentially, what you need to do, you need to move all your dots closer to your hardware, to your roof lines, right? So that's the goal of your optimization, and on every step you essentially you can track your progress, right? So that's the part what I like. And another part what I like about roofline analysis is actually, so it kind of forces you to think from the first principles. It's like you essentially ask yourself a question like, hey, how fast it can be, right? So I think that's kind of that could save you a lot of time, and really focusing on the important things first, right? And not spending a lot of time fixing some minor inefficiencies, right? So that's what I like about roofline. Okay, let's move on. Right. So before we start, fixing the code, right? It's important to collect some statistics, right? It's one of the principles of data-driven development, right? So again, thanks for Jakub, for collecting all those charts. We have in total number of words is again, right? Remember the input file is quite large, and total number of words is like roughly 500 million, so slightly more than that, I believe. And well, three important observations we could make from the input file. Well, first, majority of words occur only once. So you see 70% of all the words are unique to be precise, roughly 70%. Yeah. So and below you can see basically, well, okay, so we collect all the statistics, right? So what do we do with that? And we collect those observations actually for a reason, right? And for a reason that I put on the bottom of the slide, right? So we can use the information about uniqueness of the words for sorting, right? Because we can essentially we can regroup the words based on their frequency, right? And if we know that and the majority of words are unique, so we can put them in a separate data structure and sort them separately. So basically, that's the idea. The second observation is most of the words are shorter than 32 characters. Right. So this gives us insight into choosing the short string optimization, right? So again, okay, we have a slide on SSO later in the presentation, but just again, right? So since we don't have too many large strings, we can essentially try to keep them in the hash table entries, right? So again, that's the idea. And then the third observation is most of the words differ in the first 32 characters. Well, how does that help us? This is actually relevant for comparing strings, right? I should probably say that, well, what does it mean, right? That most of the words differ in the first 32 characters. Well, if you take a look at the chart, right? And for example, take a look at this point, right? So 45% of words differ with all the other words, and you need to identify that you just need 10 characters, right? Well, so it means that if you have 10 characters, then you have a 45% chance of the two words being different, right? Does it make sense? Any questions on that observations? By the way, I probably should say that the input itself is not what what you will maybe typically see in the large text files, because for example, if you are, let's say, reading some fiction books, right? You will not see the same observations as we have in this challenge, right? Because it will be quite unlikely that you will have a lot of unique words, right? You will usually the author of the book will use the same words over and over again, and it's quite unlikely that there will be 70% of unique words. So, but anyway, you have to collect the statistics first to figure that out, right? But why we can't compare letter by letter? You can, for sure you can. It's probably just not the most efficient way. And why 10 is specific? No, it's not. There is nothing specific in 10. It's just an example, right? You can do the same, for example, with let's say with 32, right? So if you for example take this, I don't know if you see my mouse, but if you take 30 characters, then there will be 94% probability, then that the two strings will be different, right? So if you will just compare 30 characters of first 30 characters of two different strings, right? So then you will be able to find that they are different in and the probability of you finding that is like 94%. Does it make sense? I know I might be explaining it a little bit weird, but this will not be flexible. I'm not sure I understand the comment. So again, so I think that this third chart, you will want to use this information again for how many characters you want to store in your node, right? So imagine the curve will go, for example, not the curve will not climb that that steep, right? And it will grow really slowly. Then you need much more characters, right? To store in the node and not paying penalty for accessing the for indirect memory access, right? So you don't want to pay that penalty. You want to have some amount of first of characters inside your node, right? It will speed up things pretty drastically. All right.
Can I ask here?
Sure.
Okay, I just meant that we have these observations, but I don't understand the meaning of them. I mean that in exactly this data set, yes, we can see that after 10 characters, that we can compare 10 characters and we will have the difference in 45% of words exactly in this data set, but it's not flexible. I mean, if we take another and how these observations right now can help us.
It makes perfect sense. Yeah, thanks for the comment. Indeed, I mean, well, you see, so in this challenge, you have a fixed input file, right? So and I do not ask for optimizing for any other input file. But in general, yes, you are right. In general, you cannot rely on the same observations in all the inputs, right? So if you optimize, if you will essentially run, if you will do all the optimizations that we have in this presentation, and you will run your application on any other input file, you might see the regression, right? You may even see less performance than the baseline version. So you see, I'm not saying that, but the point of the challenge is that you learn to you kind of follow the data-driven development, right? You have to know your data in order to optimize your application well. Does it make sense? If you kind of if you don't have kind of the let's say the common pattern of the input data that you see, or if you don't know that, well, then you cannot make some of the decisions that we could make in this challenge. But in this challenge, you see, we just learn to practice, right? Data-driven development. You kind of you collect a lot of statistics, and then you go from there. Does it make sense?
Yes, thank you.
Sure. All right, let's move on. Okay, optimizations. So here is the, oh yeah, and you see, so exactly the the thing that I just said. Disclaimer at the bottom of the slide. Again, no guarantee that those optimizations will help on different inputs. So, but there is a good chance actually that some of them will still help. Optimizations, and we'll have a slide essentially on every one of those. So maybe we'll not just spend too much time on this slide. Let's maybe go straight into the specific optimization. And the first one is file X, is accessing file. So we have a large file, right? And so the problem how you know how it's implemented in the standard stream in F stream, right? Is that, well, when you read the file, there will be an excessive copying, right? So you first have to allocate the file, allocate the memory space for the file, and then it will be copying, you know, by small chunks into the F stream internal data buffers, right? And only then you will kind of, you know, you will process it, you know, you using this operator. So it is inefficiently, right? Inefficiently, you need to copy the same data twice. What you could do, you could allocate you essentially you can map your file directly into your address space, right? And essentially save one copy, right? One copying. So instead of instead of copying the same data twice, you just need to copy it once. So this is the kind of, you know, the, well, pretty much basic optimization. I know many of the participants in, you know, in different contests do this trick. It saves, as I said, right? It saves saves some work that you don't need to do. And you use the mmap for that, and you basically receives the raw pointer, which you can then, you know, iterate through and just, you know, compare it, you know, character by character. So that's how you do it. So this is for Linux. If you are on Windows, this is how you do it on Windows. By the way, I actually I haven't tried it. It's just, you know, I found that in one of the solutions, but it works. It gives roughly the same speed up, and, you know, those are the APIs that you will use to do the same trick on Windows. Any questions to that slide?
Yes, may I ask? Hello?
Sure.
Yeah, doesn't this using mmap in some sense violate this one thread rule? I'm not that good in internals, but say if you have a very multi-threaded application that loads all CPUs, all cores, can this actually fire back if we use something like mmap instead of manual reading, instead of performing read ourselves?
Can it fire back? Can it fire back in terms of performance or in terms of correctness?
In terms of performance.
In terms of performance, I don't know, but why it should fire back? It's just that you allocate, you know, a whole chunk of memory in advance, right? Is that the problem? Is just, you know, because
no,
yeah,
I mean, I don't know exactly how this map happens, but isn't it a job that is done by OS itself, somewhere in background?
that's a good question.
So, I think what will happen is if the kernel recognizes that you are reading it sequentially, or if you tell it that you're going to read it sequentially, it will be loading the file into the page cache before you are done reading it. So the kernel will be doing work on your behalf, but it still has to like copy the memory once into your process's memory. And the comparison on this slide is between copying the memory twice, once into your process's memory, and then a second time from the IF stream's internal buffer into a string object, versus copying it just once from the kernel into your process's memory. So it's true that the kernel is doing work, and it would be doing that work either way.
Okay, thank you very much. This answers my question.
Cool. All right. Let's go next. That's then interesting. So that's actually text parsing, right? So now that you, well, okay, so imagine we implemented this trick with mmap, right? So then we have a raw pointer, and you can basically process it like that, right? So you can iterate through all the characters and basically compare every character one by one. Well, this will be a suboptimal implementation, I would say, right? And by the way, so this is actually what I've been using, you know, most of the time until I learned the trick with p shuffle b, which will be you know, on the next slide. But right, so essentially the idea is, well, instead of processing every character one by one, you can process 32 characters at a time. So that's the idea, right? And that's how you how you do it, you know, well, not a naive way, but you know, this is essentially a SIMD way of doing that, right? What do you do? Well, first you populate the mask, or here is an example, right, on the right. So you populate, for example, you want to separate separate the words, and you know that you know, the only separator you have is this end of line character, right? So what you do, you populate your mask with that character, right? So then you have a chunk of data that you wanna break into words. So then you compare the chunk of data with that mask, right? And this is what you have. This is what you have. You have 0 because it's not end of line character, and then you have 1, and so on. So now you need to find the positions inside that mask of well, and you basically dump that mask from the vector register into a uint 32, right? So now you need to find the position of the bits that are set in that 32-bit integer, right? So that's how you do it. You use tz count. It's essentially, I think it's a trailing 0 count. But okay, anyway, regardless of the name of the instruction, so this is an intrinsic again, which will map into an x86 instruction. And so this will give you the position of the leftmost bit set, right? So that's how you find the first set bit, and then you shift your mask to the right and find another bit set, right? So that's essentially how you process that chunk of data, right? And well, that gives you the beginning of and the end of every word, right? That makes sense. And so, and this implementation gives you roughly 2.5% 2.5x speed up compared to the you know, kind of baseline way of doing, you know, sequential way of doing parsing. Questions on that slide? I see some comments in the chat. Let me quickly try to read it. Yeah, I think the comment from Robert is regarding previous slide, right? Anyway, any questions, folks, to regarding this slide? By the way, actually, quite many people implemented, not exactly like that, but you know, something like that. All right, and now we have this p shuffle VP shuffle B trick. Jakub, do you want to go with this slide?
Yeah, sure. Just to be clear, this is not my idea. It was brought to our attention, I think, by Robert. Yeah, so this is just a really clever trick to essentially simultaneously compare against all of the white space characters at once. And the way we do this is we use the VP shove B instruction, which is behind one of the shuffle intrinsics. Oh, right, it's here at the top, the shuffle. Yeah, so just shuffle. And essentially what the intrinsic does is it shuffles the input within 128-bit lanes. And the idea is that we can use this to essentially map the white space characters to themselves and map all non-white space characters to something else. And after that, we can compare the results with the original input. And we essentially get a bit mask of the white space characters, excuse me. And yeah, to maybe dive a little bit deeper, the way the shuffle works is that you take within the 128, right? So that's 16 characters, 16 bytes. And within each of these lanes, the instruction takes the low 4 bits of the control argument, so the second one, and it returns, so at position I, essentially, it takes the ith element of the control argument, it takes the lower 4 bits of this of the ith element, and it returns whatever input was at the index corresponding to those low 4 bits, right? So here's the example on the slide. So you can see here that, for example, since the map here is at the top, and if we use our input, right? So our string here is hi, comma, white space, perf, white space, ninjas, white space. And so, for example, for the first input, this is, by the way, this is in hexadecimal, of course. So if we take H, capital H is 48 in octadecimal, in hexadecimal, and the character which is at position 8 of the mask is 0, right? And if you repeat this for everything, so here is 9. We have the tab character at 9, right? So this is a problem, which we'll get to in a second. And we do this for every character. This is essentially what we do in the shuffle instruction. So the key observation here is that we choose this map. This is a constant, right? That we define sort of a priori of everything. And this map is constructed so that the white space characters map to themselves, right? So for example, or here in the bubble on the right of map, we have the hex encoding of these characters. And so the space maps to 0, the tab character maps to 9, and the break line maps to 8, right? So that's 10. And if we do the shuffle for all of these, our entire input, we get this result in the third line. And because, of course, we only use the low 4 bits, we didn't look at the high 4 bits, we get some sort of incorrect results, right? So, for example, the lowercase I, which is 69 in hex, gets mapped to the tab character, right? Because it shares the low 4 bits. Both of them have the low 4 bits corresponding to 9. However, of course, lowercase I is not a whitespace character. So we need to do a final comparison here with the original chunk of data. Yeah, and what we get is kind of similar as to the previous slide. We just get a bit mask of where the whitespace characters are, and we proceed as before with the count trailing zeros intrinsic or instruction, or I think there's actually a compiler built in, which is maybe a bit more portable than the intrinsic, of course, but that's a detail. And I just had a slight comment, so there's no confusion about the figure, the 10x speed up at the bottom of the slide. What this refers to is I just ran a simple benchmark where we just count the number of words in the entire input file. So I just thought this would be a good sort of minimum example of the speed up this can give, because we're not really doing any extra work other than this. We're just counting all the words, right? So it's 500 million or something of that order. And if we just do that compared to the F streams, we get a 10x speed up, which I think is pretty nice. And just another maybe short comment that actually this, in the case of our word count problem, this trick does not actually give us any meaningful improvements compared to just sort of standard SIMD comparison that Dennis showed in the previous slide. But I think it's still just a really great trick, and I'm sure there are plenty of.
Oh, really? So I'm sorry. So it doesn't provide speed up over that version.
No, I think we
Yeah,
measured
doesn't
that,
help.
and it's. Yeah, sorry. I think Robert can speak a bit more.
Oh, I mean, I just tried out both of them, and I could not measure the difference between the two implementations.
I see. Then I see. You know, I mean, I think the problem is not the computation, but the problem is data. I mean, you're probably the computation is cheap in this case, and you might be limited by memory accesses. So the fact that you're processing characters faster doesn't make any difference in this case. Maybe.
Yeah, I think it's just like a back of the envelope calculation. We can benchmark, or I benchmark this against the thing from the previous slide, and I think it's for just parsing out the white spaces. This takes like 3 cycles per 64 byte chunk, and the one from the previous slide takes 5. So we're saving essentially 2 instructions per.
Yeah, I'm sorry. Yeah, one important thing here actually, but you see here in this version, you actually have to repeat it 3 times, right? Because you have three character separators, right? You have white space, tab, and the end of line. So you have to do the same 3 times, right? And here what I'm sorry. Here's what I tried to capture in the comment at the bottom of the slide, right? And yeah, just to be fair, again, I measured the speed up actually. So it is one of the lab assignments in my Performance Ninja course. So that's the speed up where I took. But again, it's not. So this speed up is not applicable to the word count. Again, it's just the speed up on a synthesized benchmark.
Hi guys,
Yeah,
I have a question. This is Yuri speaking, Yuri Lifenko. When I did this exercise, I actually decided that the best way to split the words is to just exclude the range from 0 to 32 inclusive. And this seems to be faster. You basically just use a single CMP greater than. You only need to shift it up so that to account for signed, unsigned. And I basically discovered the range, the borders of the words just by excluding the symbols from 0 to 32. Is it the wrong approach? Because it seems to work with the data set that was provided. And
Wow.
it looks like it's faster than the approach described on the last slide, and I did the measurements.
I cannot comment on that. If anyone of, if Robert or Jakob, well, I mean, so essentially you are saying that you don't need to do all this trickery. You can just essentially compare if the character is less than 32.
Yep.
Then it's a separator.
Yes.
Wow. Well, I mean, again, it will not work in general, but if this works for this data set, it's an XML file, right? So, well, interesting. Yeah, it's interesting.
Yeah, I mean, I think this is one of those cases where the simplest solution is the best. So yeah, but I just think as a kind of not specific to this challenge, but just in general, I just thought I was honestly just blown away by how clever this the shuffle trick is. So I think that's kind of why I wanted to spotlight.
Mm-hmm. Yeah. Yeah. By the way, I like, to all the people on the call, if you don't understand this trick, don't worry. It took me 30 minutes to understand it, and I'm still quite not sure that I fully understand this solution. Like, for example, and actually maybe this will be a question to Jakub or Robert. So how do I populate my mask if, say, I have additional separators? So what do I do? So like, why the mask is constructed this way?
So I think that there's Wojtek Mula has I'm probably butchering his name. He has a pretty good post about this. I would like to make another post that is slightly better one day, but his is the best on the internet right now, and I will just post that in the chat. So you can just read that. But what you would do if you wanted to add like one character? My first question for you would be, does that character differ from all these other characters in the lower nibble? And does that character not have the high bit set? And if your answer to both of those questions is yes, then what you would do is you would find the position in the map vector that character goes in, and you would just put that character there instead of 0. So if you wanted to exclude character number 15, 0x0f, whatever that is, you would just put that in the F slot, and then you would now have a table that filters for those 4 characters. If you wanted to add a character whose lower nibble is A, then you would have more trouble.
Mm-hmm. Yeah. Well, okay. So essentially, what you're saying is that there could be a situation where 2 separator characters will compete for the same space in the mask, but I can always do a second mask, right?
Yes, you can do a second mask, or you can try to find some function that takes only one instruction to compute that will give you like a different 4-byte range into the bytes that is unique, instead of the bottom 4 bytes that are not unique.
Mm-hmm.
But this is like very silly stuff. I don't think that anyone needs to think about it. I really like the explanation that Jakub was able to give about this instruction. I've had a hard time understanding it myself. I think the best way to come at it is actually to not do this stuff, and instead to use it normally. The way that you use this instruction normally is that you would put the input that you're reading from the file into the first argument, and you would put a constant value into the second argument, and you would be saying, I'm using this constant value to rearrange some of the bytes and to zero out some of the other bytes. For example, I'm doing some integer parsing problem on some other website, and I need to like spread out. Maybe I have like 10 bytes worth of ASCII integer data, and I want to like spread it out so that it occupies the bottom 3 out of each 4 slots within the lane. And so you can use pshuffb with a constant value for the control and the first argument equal to the input from the file to do that. This thing where you use the input as the control and a constant as the first argument is very weird. You're saying, I want to use the input from the file as the indices into a lookup table that I have already computed ahead of time.
Mm-hmm. Okay, well, good. Any other questions regarding these slides or the previous one? Yeah, this is SIMD is tricky stuff, and and it's but it's good that we have like a patterns for the for specific problems. So that's good. Oh yeah, and yeah, Robert, please please put a link to for the Wojciech website for the article that you mentioned. All right, let's move on. And this is right. So now we're actually moving. We've done with parsing. Now we're moving into hashing. Well, and I would like to open actually another discussion about what are the the benefits of using particular hash table, particular hash function. When I try to capture some of the design goals and trade-offs, but again, you guys are the experts here. You've done experiments, you've tried different things, but yeah, I think one of the probably kind of most proven ideas is that you definitely want to have an open addressing hash table, right? And then so this is regarding hash tables, right? Well, I don't think and you guys can correct me if I'm wrong, but I don't think that the particular implementation of the hash table matters, right? I mean, besides, of course, the whether you want to have this chaining or kind of open addressing hash table, but besides of that, I don't think that makes much difference. And again, you can correct me if I'm wrong. But regarding hash function, this is, I think, where it gets more interesting. Is that, well, you want to have as less as fewer collisions as possible, right? And at the same time, you want to have the fastest. You want to compute hash quicker, right? And those are two conflicting things, because the more bits you kind of or let's say the better hash function you select, it might be slower. So that there is a trade-off, right? Whether you want to avoid collisions and avoid comparing strings and use a more expensive hash function, or you are saying that, well, okay, computing hash is cheap. I can I can better or no, I mean vice versa, right? So or you're saying, well, okay, computing hash is expensive, so I am kind of allowing collisions, and I want to have as fast as as hash function as possible. Oh yeah, and then another consideration here is that, well, you want to have as fewer bits as possible in case you want to store a hash inside the node. Does it make sense? So guys, okay, but well, I think one of the observations someone mentioned in Discord chat is that some of the hash functions will give you absolutely zero collisions, right? I think those are which one? Those are FNV. I think the Andre used it in his solution, and I think WY hash. I think it's right, Robert. It will also give you zero collisions.
Yeah.
Okay. Well, so maybe you guys can comment, right? So how important is is like this particular thing? So how it affects performance? And there's silence.
So I want to go back to an earlier point about the hash table implementation. I actually think this is pretty important. I think that it's important how many accesses you need to do on a very typical insert, an insert that is not having, well, I don't want to ramble too much, but if almost all of your inserts are of one kind, you care about sort of how many cache lines that kind of insert has to touch. If you are using Swiss tables, it will almost always touch two of them. One to look up where to look for the actual slot of the thing, and then a second one to look up the actual thing. If you are using Robinhood tables, then maybe it only has to touch one if you do not have a lot of collisions. The size of your entries also matters for this, because when you do have collisions, if they are only 16 bytes or 8 bytes or something, then you can usually fit the secondary lookups into the same cache line. For hash functions, I think that it makes intuitive sense that there would be like a quality to time trade-off. But I think that for like the level of quality that we care about, which is like not quite cryptographically secure hash functions, some of the best hash functions available are also some of the fastest. A-hash is not on this list, but A-hash I think is better than all of these functions at being fast for large numbers of small strings. And Y-hash is also very good at that. And those, I think, both would generate no collisions for the inputs that we used. CRC32 is probably faster to calculate if you use hardware support, though.
Sure. All right, good. Other questions regarding this slide? Anything I forgot to mention? India, we'll have a slide about SSO. Oh, okay.
I have one comment, rather a suggestion. If you need to hash a short string up to 16 characters, at some time I came up with a neat trick that does it in basically 2 instructions. I'm posting it in the chat. So basically I'm using the AES encryption decryption instructions for cryptographic strengths. It is recommended to do 10 translations like this. But if you are only looking for a hash to minimize the number of collisions, this one gives just 2 instructions give you a pretty good distribution. The constant here is just a set of random numbers. They don't mean anything. So if you have a string from 1 to 16 characters, it'll give you a nicely distributed hash that you can use as a key in your hash map.
Wow, that's nice. Cool. Yeah, so you see there are a lot of options. Yeah, well, good.
I
All right.
have actually a quick question for Robert or anyone else who would care to jump in. You mentioned the size of the nodes or the things that you're actually keeping in your hash map. And I was wondering if you maybe had any quantitative data on how this affects the performance, because, and again, this is kind of very non-precise, but I kind of noticed that the size of the things that I was keeping in my hash map didn't matter as much because the access pattern was random enough that spatial locality wasn't really helping me out, right? So I was hitting different cache lines all the time, essentially, is what I'm trying to say. And you mentioned this, and I was wondering if maybe my observations were wrong, or if you could maybe briefly speak to that a little bit.
No, you're correct. So this sort of only matters in a very narrow case where, let's say that you do have 2 keys contending for the same slot. One of them has been bumped to the next slot. If your entries are like twice as wide, then your odds of that next slot being the next cache line go up. There's no real like spatial locality benefit other than that. And
Okay.
I don't have like measurements about this issue in particular. What I did do is I tried taking my implementation and making the hash table entries much larger, so that I could cache more bytes from the string, which we'll talk about later. And I found that it slowed things down, but I don't have any like metrics about this particular thing on its own.
Okay, thank you so much.
I want to share another trick that I did. I don't know if I'm stating the obvious, but when I calculated hashes, I calculated not one, but 64 hashes at a time. And after calculating the hash, I calculated the position in the hash table and prefetched it. And only after that, after this processing the whole batch, I would just go and insert it into the hash table. That seemed to speed it up a bit.
Yep, and I think I have a slide on that. Yeah.
Okay.
Yeah, but thanks. Yeah. All right, let's move on. Yeah, so this is just, this is a high level trick, maybe, if you will. It comes from the observations that, well, first, most of the words are short and unique, right? So when we actually parsing words, we can kind of, keep them in a separate data structure, right? So that's basically all it is about. So and again, you can implement it in different ways. You can you can classify different words based on different things, not just on their lengths, let's say. I don't know, but or you can maybe put the threshold differently, right? So for example, you can say, well, I don't want to just keep the unique words, but I also want to keep unique and, for example, the words that occur, let's say, 2 or 3 times, right? And the same goes for the length of the string. You can say, hey, you can basically define what it means for you short, right? So, and here I just show you an example, right? So you can keep the single letter and 2-letter words in just basically in separate arrays, right? And for keeping a single letter words, you just need 256 size. Well, an array of size 256, right? So it's really tiny. But for the 2-letter words, you basically need 256 multiplied by 256. A lot more bigger than that. But still, it is how much? Let me do a quick math here. It is 64K, right? 64K of, well, 64K multiplied by maybe 8 bytes. Oh no. Anyway, sorry guys, I have to do the math in my head right now. But anyway, it is definitely like less than megabyte. So not much memory compared that that we already occupy a huge amount of RAM for this particular workload. What does it give you? Well, you can well, if you keep them separately, you can essentially even process them separately and then combine, right? So for example, these for example, those 2 arrays are super easy to sort, right? But then what about the unique words? Well, the good thing about unique words that you already know their frequencies, right? And so they already partially sorted. So that's the benefit. And then you can keep all the rest of the words in the general in the common hash table, right? So yeah, that's the idea. Again, many different implementations. Actually, I was looking at the solutions, and they all tend to follow this, but but the thresholds are different. Okay. Any questions to that? I think this is pretty basic stuff. All right, now let's actually talk about the small string optimization, right? Well, and the idea is pretty simple, right? So if the string is large, but we know that most of the strings are actually small, right? But if the string is large, then you have to and if you keep in the node, in the entry of the hash table, if you keep, for example, a pointer to a string, right? Then every time you will need to to essentially fetch this memory location, right? And it's expensive. So obviously you want to avoid that, but you have to store some of the characters in that entry. So what are the implications? Well, the implications are that your hash table grows. Well, obviously, right? So you need to carefully select how much data you want to store in every entry. But there are benefits as well, right? So for example, if you for example store the strings that are less than 32 bytes in your entry, then once you have a collision, you can compare them super fast, right? Again, you don't have to pay the penalty of the memory indirection, right? Because you don't have to fetch the string from memory, right? You don't have to go through the pointer, which will and there is a certain chance that it's not in the cache, right? Because again, remember your hash table is super large, and pretty much every access is random, and will miss in caches. All right, so that's just an idea how you can speed up the comparisons. Basically, if you, for example, store 32 bytes, first 32 bytes of a string, well, actually the entire string that are less than 32 bytes. If you store them inside the node, inside the hash table node, then you can compare them just by using comparison of the two YMM registers. It's super cheap. Well, that's one of the ideas. And then another idea actually comes from Robert. Inside, well, I'm sorry. Instead of keeping the string, you can actually use a reversible hash, right? So and if the length of the string is small, it's less than 8 bytes, then you can keep it not as a string but as a uint64, right? So uint64 is 8 bytes. You can just store it as integer. But then if you compute a hash, then you can recover the initial string from the hash, right? So that's, again, that I think is a clever trick.
I'm sorry, it's not clear to me. Why do we need to convert it to a reversible hash if we can use the same short string as a key and compare it directly? You just cast it to uint64 and compare. Am I missing something?
I think I would get more collisions if I did that.
Well, the different strings are unique by definitions, because they are
Yes.
different.
I agree. For this hash table, I think I am like shifting out almost all of the bytes, almost all of the bits, and I'm only using like the first 3 bytes and maybe missing one of the bits out of one of those bytes as well. So I have to mix it somehow.
Okay.
All right. Any other comments regarding this slide? Again, so guys, so actually, Robert, yeah, thank you for correcting me. I might be missing something. I might be capturing your ideas wrongly. So whenever you see I'm doing that, so feel free to correct me.
Oh, this is all right. This is a hash that's based on fx hash. I was trying to use fx hash fairly early in working on this problem. It didn't work out, but I kept it for small strings because it's reversible.
Good. Oh yeah, so that's actually the slide, Yuri, that you're asking about. So this is regarding hash table prefetching. So here I'm showing you only only like well, let's say the basic idea, right? You can implement, you know, let's say you can come up with a more sophisticated implementation. It's just the basic idea, right? Well, it comes from observation that, well, the cache misses are inevitable. I mean, you are accessing the hash table randomly, right? So it's just no question you will have cache misses. But what you can do, you can actually try to hide the latency of those cache misses. For example, and here's just one of the example, right? If you can essentially what you can do, you can batch all the cache misses, you know, together. So essentially, like, you know, pay the penalty once for a small chunk of data, right? So prefetch like essentially everything into the cache and then process it. Or you can even go more complicated than that, and you try to overlap the fetching of data. I'm sorry, the prefetching the data that will need to be used later with the computation, right? So if you take a look at the picture here, right, at the figure, okay, so it, and that's the timeline, right? So what you can do, you can, for example, when you parse a word, you compute the hash for it, right? And then you do not process it right now, but you prefetch a bucket which the string will go to, right? So that's the idea, right? And then you continue, right? So you parse the word B, you parse the word C, and then you after some time, and you need to carefully, actually, you know, carefully choose this look ahead size, right? So how much words you want to process before you actually start to try and insert them into the hash table. So that's basically the idea, right? And here is the pseudocode for it, right? Again, I'm showing you here the, well, maybe the simplest way to implement it, right? But the idea is this: so you parse, so you process a chunk of data. Let's say, I don't know, 256 kilobytes, right? Again, what are the considerations? You have to select it carefully, that, you know, that the data that you prefetch will sit in the cache, you know, and will not be evicted by anything else. You can adjust it for L1 or L2 cache sizes. It's kind of tunable, right? So you need to try the thresholds, different values for the thresholds. So then once you parse all the words, you compute the hashes for them, right? And then you prefetch all the memory locations, right? And then you kind of, you know, store that, you know, into you put them in the list, right, which will consist of pairs of words and hashes, and then you basically process that you know, that collection, and you insert all the words. But the good thing here is that there is a chance that by the time you need to actually to access that memory location, it will be already in the cache, right? So that's the goal. And let me see considerations. Many words. Oh yeah. So the thing I wanted to say in the first bullet point in considerations is that there might be a situation where you parse a chunk of data and there are not many words in it, right? I mean, if you actually take a look at the previous, you know, slides with observations, there are still quite long words. So if in the given chunk there are not many words, then, you know, it might be not that efficient. But if you process the chunk and there are a lot of words, then the prefetching is, you know, will help you a lot here. Then oh yeah, so as I said, right, the size of the chunk is basically tunable. You have to tune it. Oh yeah, and then so then the idea is that the third idea is that, well, you know, so in the pseudocode on the left, right, so you can see there is no overlap, right? So we do not overlap insertions with the prefetching, right? So although so and this one is easier to implement, but if you want to overlap actually really like overlap it truly, then implementation probably will be a little bit more complicated. Any questions to that? Yeah, and the assumption and the assumption actually that we are making here is that, well, parsing a word and computing its hash is pretty cheap. Well, why is that? Is because, well, when you parsing a word, you process the input file sequentially, right? So there are like no micro architectural problems in this case, right? You process sequentially. Computing hash is relatively cheap compared to the latency of the L3 cache miss, right? So the insertion part is expensive, right? So because, well, we're talking about 300 cycles plus. That's kind of the latency of fetching a memory, fetching a DRAM location. Any questions? If not, we can go to the next slide. I don't see any questions. All right, let's go. Yeah, so utilizing large pages. Okay, let me maybe step back a little and give give some background for those who know this stuff. I'm sorry, I just want to give a little introduction here. Why does it matter, and what's going on here with the large pages? So remember, right? We like in your program, right? You only have virtual addresses, right? But when you actually want to fetch some data from memory, you need to physical address, right? And the CPU is done, is doing that for you, right? It's doing virtual to physical translations, right? Now, the memory is obviously broken down into pages. The default size of the page in memory is 4 kilobytes. On x86 on ARM it's actually 16 kilobytes, so slightly, well, not slightly, 4 times more. But so, and essentially every address is broken down into like the leftmost bits are the page address, and then the right and then the right part of the address is the offset inside this inside that page, right? So that's how your CPU is doing translation, right? You don't need to translate, you don't need to change the least significant bins. You need to translate the most significant bins for the page address. And translation, like, well, what does it mean to do a translation, right? So the kernel keeps all the mappings from virtual to physical addresses in its page tables, right? And if you don't know the physical address for the virtual, you need to go and walk the page table, right? So this is what it calls, a page walk. So and it is super expensive. It's like we're talking about 1,000 cycles, right? Obviously, you don't want to do that. But the good thing here, well, okay, so and keep in mind that, well, before we had actually hardware support for a page walks, what do you do if you miss, like if you don't have a translation for a given address, you have to you have to generate an interrupt, right? Then the CPU will then the OS will handle this interrupt. So it's like, so from that point we're talking about 5,000 cycles, like, but now we have a hardware support. So what does it mean? It means that when a CPU doesn't have a translation for an address, it will do a hardware page walk, right? So there is a hardware, so the hardware itself issues, the micro operations and will walk the entire page table will fetch like without an interrupt, right? But still, it's 1,000 cycles, right? So it's pretty expensive. To mitigate that, in the CPU, we essentially what we can do, we can cache the translations, right? And sorry, I'm like, that's a long introduction, much longer than I than I wanted, but anyway. And sorry about that for folks who already know this stuff. It's just I think it will be useful for the folks who will watch it later in the recording and might not know this. So there is a similar cache as you cache your data or instructions. You can as well cache the translations. And this is what obviously most of the modern CPUs are doing. So they cache virtual to physical page translations, right? In a cache that's called TLB, that's translation look-aside buffer. So there is data TLB and instruction TLB. But the thing here is that, well, because you see, because the page size is, well, pretty small, I would say it's 4 kilobytes, right? And so to map to for example, to map and yeah, I have an example on the bottom of the slide, right? So imagine we have like a hash table that is 1.5 gigabytes large, right? So you can calculate how many page tables you need to cover that space, right? It will be a lot, and and it will obviously not fit into the TLB cache. So what you could do, you could actually you could use a huge tables. So the huge tables is a feature that is supported by well, I should say that it is actually dictated by a CPU, right? So the you should guys remember that. So the format of the page table is dictated by the CPU. So whatever is supported by CPU, it can be supported by the software. I mean by the Linux kernel or Windows kernel, whatever. But so the available page sizes on x86 are 4 kilobytes, and then you jump straight into 2 megabytes, and then there are even larger 1 gigabytes huge pages. Okay, so to map the same address space, let's say 1.5 gigabytes with 2 megabytes pages, right? You need 500 times less entries in your cache, right? So this makes much more efficient use of your translation look-aside buffer, right? So that's the whole point of this optimization. Yeah, I think, and that's how you do it on Linux. You essentially use the same mmap. So the idea here is that you allocate your hash table, and you use large pages for that allocation. Make sense? So let me see, what else should I say here? Yeah. So on the right, you can actually see, so and this is, by the way, this speed up that is applicable to word count, right? So I took this speed up by measuring, like with huge pages and without on one of the solutions. I don't remember which one I used specifically, but yeah. So if you just use, for example, perfstat, and you want to collect the absolute number of those TLB loads and TLB load misses, so that's what you will typically see. Well, you can say, we go down from 1.9% down to almost 0% TLB misses, but you see it makes a huge difference. And remember, every miss in a TLB cache is super expensive. It's like we're talking about 1,000 cycles. Yeah, I think that's pretty much it. Let me see. Oh yeah, I don't have a slide about large pages on Windows, but you can do the same on Windows. It's just a little trickier than on Linux. you have to mess up with the security policies and you know, so I don't know why, you know, Windows makes it harder for you, you know, to use huge pages, but it is what it is. Yeah. Any questions, guys, regarding this slide? I hope it was not too long. Can you hear me?
Yes, we
Yeah,
can
yeah.
hear you. Yeah, just everything is clear. No comments.
Wow. That's good. I see a comment from Chad. Anyone do dump bucketing
I just wonder
merge
if
sort?
anybody tried to do like a bucketing merge sort and then just do the hashing stuff at the end once you have smaller size buckets.
Why do you think, Chad, it will be faster?
Because you're keeping everything in cache for a lot of it.
All right, let's maybe actually. So I think we'll next go into sorting. So that's our last part, and then maybe we can discuss it there. But I haven't seen actually anyone implementing merge sort.
Well, kind of like a merge sort, but basically just start with a number of buckets and fill them up. Like just take a 64K chunk, sort it like you normally would, and then split it out into a number of buckets that you have. And then if one bucket fills up, replace it with 2 buckets by splitting the range. So you're kind of adapting to the distribution of the data. And then you'll just have a tree of sorted buckets. And then you just do a merge sort on that tree. And each bucket will have 64K sorted.
Okay, Chad. Well, it looks like a good thing you know, to try for you.
Well, that's kind of how David Bader back in like the 2000 or 1990s did a lot of these bucketing sort type things. And the adaptive thing is kind of something that Tarjan did.
It's nice. Well, if you have time, you can maybe, you know, implement and then, you know, just let us know. It'll be fun to look at. All right, let's move on. Hybrid sorting. Oh yeah, I think this is just, you know, just again, pretty high level idea. Don't want to spend too much time on that, but so it comes from the observation that the most words are unique, and then the idea is to essentially, you know, bucketize the words based on the number of their frequencies. So essentially, like when we dump the data from the hash table, like into some other data structure, into the sequential data structure for sorting, well, you can already use that step and you know, and make use of the fact that you can bucketize it and essentially have the data already partially sorted, right? And this way you only have to sort them lexicographically, which is still, by the way, probably the most expensive part of the sorting, right? Oh yeah, then the second idea is that maybe then you know, Jakub can jump in as well, but so it comes from the thing that, remember, we can store the short strings inside the node, right? And then if we store them, you know, and then we can use SIMD instructions instead of just, you know, simple comparison of strings to speed up comparison. And Jakub, do you wanna go through specific implementation of that?
Yeah, sure. I mean, I think it's fortunately much more straightforward than the previous SIMD thing we were talking about. But this is basically just a SIMD lexicographical comparison of 2 strings or 2 YMM registers, I guess. And the idea is simply that we want to get the bit mask, which signifies where the two words diverge, so the not equal mask, and a bit mask, which tells us the greater than relationship. And then we can, as with word parsing, use the count trailing zeros instruction or intrinsic or whatever else, and just get basically get the position of the place where the words first differ. So the least significant, the position of the least significant one of the not equal mask. And we can also get this position for the greater than relationship. And essentially, if the position where the words are first not equal is smaller, oh, excuse me, there's a dog barking in the background. Apologies. If the position of the, let me close my window 1 second. Sorry about that, guys. So just very simply, if the position where the words are not equal is smaller than the position where they're first, where the greater mask has its first one, then we can tell that the first word is less than the second word in the lexicographical sense. Yeah, I mean, you can look at the code. It's really not complicated at all. Just a small comment here that what we need to do is for the individual characters is an unsigned comparison, and there are actually no instructions for that in AVX and AVX2. So you need to do you need to compare with the minimum of the two vectors to essentially get this unsigned comparison, because there is an unsigned minimum instruction. And maybe a very small note on that, actually in AVX 512, they added, or Intel added unsigned comparison. So, you know, maybe if we could, if we had access to that hardware, we could potentially do this faster. And yeah, just another small note that this is actually a completely branchless comparison. Obviously, you need to branch on the results of this. But the comparison itself does not contain any branches. So it's blazingly fast. And this is the approach I used in my sort, which, I mean, wasn't obviously the fastest solution. So maybe take this with a grain of salt. But basically the idea is that if you can store a buffer of the leading characters, so I think in my case it was 28, but this is just a tunable parameter. Then you can do a first pass where you just sort only according to these first n characters. And as it turns out, because of this observation that we made at the beginning, that most of the words basically differ in their initial characters, after you do this first pass, most of the words are actually sorted. So then you only need to do a sort of full sort with only a few words. And what this does for you is it avoids a whole lot of pointer indirection, because you don't actually need to you know, take the penalty of looking at the remainder of the word to do this comparison. Yeah, so I think that covers it.
Cool. And I think Jakub, well, I mean, okay, well, your solution was not the fastest, but I think your sorting part was one of the fastest, if not the fastest.
I think all glory goes to Robert here. I think the radix beat me out by a little bit.
Okay. Yeah. All right. Let's move on. Yeah, just I think we're actually pretty much at the end of the presentation, so that's good. We don't have I think we have only 2 or 3 slides left. So just you know, high level other sorting ideas. Again, what I was able to capture from your solutions, guys, is just I saw, you know, folks are using representing small strings as an integer and doing and comparing basically short strings as an integer. And here is an example how you can do this. If imagine we have two 4-byte strings, well, if you represent them using int32, then you can you can basically do the comparison with an integers. The caveat here, yes, is that once you store those integers in your node and you are reading them from memory, then you need to convert, you need to do this little endian to big endian comparison. You can do this. I think it's simple. It's pretty cheap still, using bswap instruction, which essentially swaps all the bytes, which will do this conversion for you. Then the next idea is, it's just a broad, I think, broad general kind of description is just try and use the different sorting algorithm other than just standard C++ standard library sort. One of the solutions was using PDQ sort, which is which is kind of a drop-in replacement for standard sort, but looks like it gives better performance. I haven't actually used it myself, but I definitely saw it. I think it's it also, I think there is implementation of branchless quicksort inside this PDQ sort. You have to turn on the option to use it. And then we have a radix sort. And maybe again, guys, I'm opening the discussion here for you. Do we have like a best the best way of implementing sorting? What are the proven techniques here for this particular workload?
I really don't know. So I tried a few things, and the best thing that I found was an adaptive radix sort. I think that if I were to use the bucketizing well aggregating that Jakub had used, I would gain some speed there. And I think that Google recently published a paper about their branchless SIMD quicksort that has a sorting network for the base case that is supposed to be pretty good at sorting 128-bit integers. And so my hash table entries could be rearranged a little bit to be viewed as 128-bit integers, and then I could use this thing to sort them. I haven't tried that. So it could be that you go faster if you do that. I have no idea. I ended up using a adaptive radix sort that processes 2 bytes at a time until the number of strings being compared gets pretty small, and it processes 1 byte at a time. And when it needs to fetch more bytes, it fetches 8 bytes at a time.
Mm-hmm. Okay, cool. Well, Chad, you can try, and implement merge sort. Maybe you will beat.
Oh, I just linked because it looks like the high performance computing people and the algorithms people don't seem to like to cite each other. So if you look for references to that paper in the high performance computing literature, you'll see more of the things that the algorithms literature doesn't cite to, and vice versa.
Okay. That's nice. All right, let me quickly see. Oh yeah, so this is actually the last slide that we have for optimization. So anything else me and I forgot to cover? Anything else that you guys want to revisit maybe?
This is a very small thing, but I was wondering if anyone has any success with using huge pages, not just for the hash map allocation, but also to actually nmap the input file itself into the address space using huge pages, and whether that gave any speed up.
So I'm doing this, but I haven't compared to not doing it.
Mm-hmm.
Okay,
This is an interesting question, Jakub. Yeah, and okay, I can only speculate, but based on what I see here, and you know, and just I think if you think about it, right, we accessing it sequentially. So why would we have problems, you know, with the you know TLB there? I mean, you do the translation sequentially. Well, so and this is actually captured. This data is captured from a real solution, right? And you can see how using large pages for hash map allocation actually pretty much, you know, it goes down to 0. So I mean, yes, it is maybe still some headroom, and maybe it will help as well. I don't know, but maybe not by a lot, because you see it's already almost 0.
Is there an easy way to pin like 64K to like L2 or L3 so you can keep on using that as scratch space?
I'm sorry, I don't think I get it.
Well, like you just want to have like a 64K scratch space in cache that never goes back out to RAM. Like the operating system knows not to touch it. Or is that not allowable in the memory model?
I mean, you are asking if you can allocate space in the cache. It is possible. Yeah, it is possible.
Yeah, just like 64K that I will always know that it's never going to page it out to RAM.
Okay, Chad, sorry. So you are not talking about using large pages right now, right?
No, I'm talking about like I have a 64K buffer and I would like to keep it on the CPU's cache and not have it go to RAM unless I explicitly copy it.
Mm-hmm. Well,
is that possible? I was unaware that you can actually. I wasn't aware of any instructions which essentially explicitly determine cache behavior.
No,
well,
I think it's defined in hardware, and there's no way you can control it. I mean, cache eviction policies, they're not controllable from software.
Cache eviction policies, I'm not sure, but I'm pretty sure you can reserve some space in the cache. There are libraries, yeah. There are libraries that allow you to do this. I will find the link and post them in the chat later. Yeah, sure. You know, obviously you'll have to have you know, root access. That's you know, 100%. But it is possible. Yeah, it is possible. You know, I saw people doing it. Yeah. It actually also helps, especially when you are in a NUMA environment. Then you know, you don't want to, you know, you want to like allocate, you know, some you know, specific amount of memory in, for example, in L3 cache, which is shared you know, with all the cores in one CPU, right? And you want to, you know, you don't want to like let the cores go into remote memory, so that's why you allocate, you know, some size in L3 cache in this particular CPU, physical CPU, right? And you essentially, that's how you can guarantee that there will be no you know, remote memory accesses. Well, anyway, I will try to find the link and share with you guys.
Yeah, actually, I'm seeing some stuff with the Intel MPI library that it supports some NUMA type stuff.
Okay. Well, so this is the again, the purpose of this slide is just to, you know, is just to prove that, you know, there is plenty of room at the top, right? You can see how the baseline version is, you know, is underperforms, and you know, and not even hitting like the DRAM bandwidth, right? For example, even like the top hotspot, which is on the left figure in red. It's, you know, it's pretty much performing really bad. But if you can see actually one on the top solution, then well, it is close to hitting the maximum capabilities of a single CPU thread, right? Again, just to mention, just to kind of emphasize that this is a single core, right? If you will take a look at the roof lines of the whole well, of the whole CPU, then of course the roof lines will be much higher, but then you can scale it even more if you parallelize it and so on. And yeah, basically this is the score table for the challenge, right? The top solution, and well, by the way, congratulations to to Robert, Stellaris, Andre, and Jakub and other folks. Really good results, guys. I'm really impressed what you have done. 12x speed up is like really impressive. I don't know. It's just like so now whenever you will see someone like implementing a baseline like solution in lead code, now that you can do even like not 5%, not 10%, but you can do like 1,000% better than the baseline, right? Okay, you can take a look at the table. I will give you some time. I basically try to aggregate all the optimizations different participants have done and put them in a single table, so so that you will see which people done what. And yeah, so the code is available. You can basically take a look at any of those solutions if you go and use this link at the bottom of the slide. They are all buildable. You can run it on your machine and see what's best for you. Any questions here, guys? All right, so that's actually the end of the presentation. Well, I just wanna say thank you to all to all the folks who participated and sent me the solutions. This was, I hope it was interesting to you and at the same time useful as well. And I hope you learned a lot. I certainly did myself. And yeah, thanks a lot. I would really appreciate it if you can spend some time and and take this short survey that I prepared. But besides from that, yep, thank you very much. If you have any comments, questions, then yeah, let me know. Let me know what you think about those challenges. Please share your feedback. Yeah. I don't have any particular plans for the next challenges. It is time consuming for sure. Taking finding a good benchmark and a good workload is not easy. It takes a lot of time, and well, and if anyone wants to help, then I'm 100% open for it.